طيب بسم الله الرحمن الرحيم. So we started chapter 9 talking about IPsec and we talked about the benefits of IPsec providing secure tunnel over a public infrastructure like the internet. We talked about the usages of this, securing communication between two offices. We talked about the fact that IPsec itself is seamlessly provides secure communication for all the traffic coming from a private network to another network or from a host to host. So we talked about two modes. We talked about the transport mode, providing secure communication between two hosts, or the tunnel mode, which provides secure communication between host and a network or between two different networks. We talked about the security association, providing the security context, which provides one-way security context because of the fact that IP itself is unreliable and provides connectionless behavior, in which case we need to provide one-way security association for each direction. And this security association is actually also initiated from the security policy database. So when the traffic comes in, we talked about the algorithm for the outbound traffic. When the traffic comes in, first we check the security policy database. We try to find a match for this particular traffic using the traffic selectors. We talked about selectors, whether it uses a combination of source address, destination address, ports, user ID, things like that. So based on these selectors, we try to find a match in the security policy database for this traffic. If we find a match, then we use the security parameter index in the security policy database to point to the security association. And then we go to the security association database to try to fetch the security association and use that for securing the communication. If there is a match but there is no security association yet, then we have to trigger the security association negotiation through IKE, which is what we will talk about today. Also, because of the fact that IP is unreliable, we cannot use simply sequence numbers for replay attacks, in which case we talked about this window mechanism to try to provide a mechanism specially designed for IPsec, working over IP, and due to the the feature of IP being unreliable and connectionless. So again, we talked about so that there's nothing new here. So we talked about the transport mode, which provides secure communication between two hosts. So here, the original IP header, okay, is exposed, and it remains the same because of the fact that the source and the destination who are communicating together, they have the same IP. So in which case, what we need to do for the transport layer is like we have the payloads, and here we have to add AH and or possibly ESP headers, okay, over the IP. So here we can use the original IP header exposed, and it's not to be encrypted or so parts of it can be used for authentication as part of the H header, as we said before, but it's not encrypted, and that makes sense because the original IP header maintains the source IP and the destination IP, which matches the source IP and the destination IP of the host. So it's a host-to-host communication. So there's no issue here. So for the tunnel mode, on the other side, tunnel mode provides secure communication between network to network or host to network. In which case, we have to use the IP address of the router or the firewall on the other side. In which case, the source address and the destination address in the original IP header changes, right? So in that case, what we need to do is that we, in addition to the payload, Then we add the original IP header. Okay, and then after this, we have to add the ESP and possibly AH. The order of them, by the way, we'll talk about it today. The order of them does not make a significant difference. And then we have to add the outer IP header. Okay. So that outer IP header will actually maintain the IP address of the source and destination routers or firewalls, which are different from the source and destination IP addresses of the hosts who are trying to communicate. Okay, so these are the two modes. So so between each two networks, we have to establish a secure tunnel to provide the secure communication between two offices. As you can see, we'll talk about it today. Actually, so if you have only if you want to secure only two offices, so it's actually one tunnel. But if you want to secure the communication amongst different offices which are distributed, مثلا in geographical locations, then you have to provide a mesh-like tunnel connections, as you can see here. So that depends on the configuration that you want to have. So again, nothing is new here. I actually omitted here the encapsulation for IPsec version 6. Okay, due to the fact that at least some of us, or actually most of us, did not go through IP version 6. So the encapsulation here is much more complicated in the standard. So I omitted that. But other than this, we notice here that ESP header here can be used to provide both authentication and encryption. So we talked about this last time. So if we are talking about IPsec version 2, so ESP can in fact be used for both, and we don't have to use AH. So AH in IP version 2 is in fact optional, so we don't have to use it, but it's actually provided for backward compatibility with IPsec version 1. And as we will see today, this also reduces the overhead in terms of security association creation. So the creation of security association here, we establish one security association for ASP. We don't have to establish two security associations, one for ASP and one for AH, which reduces the overhead, of course. And that makes sense. That's what has been introduced as part of IPsec version 2. So one thing we notice here is that here we have two trailers. Okay? As we, in network 1, we have talked to you about the fact that the only layer that adds a trailer is which layer? هتفكر؟ لا. For all the layers, in fact, there is a header, but there's no trailer, with the only exception of which layer? ايوه اللي هي لا مش الماك ادرس في الهيدر, but in fact الداتا لينك layer adds a trailer, right? But that's not talking about security. So here in IPsec we also use a trailer. So of course trailer in that case, it makes sense because for authentication you need a MAC. So we know that we need MAC, message authentication codes for authentication for the messages. So ESP authentication here refers to the MAC, right? But what is this? ESP trailer. Can you guess? For La. This is for the message format. It's part of the message format. So we know that ESP authentication is for MAC. Okay. For? لا هو الماك is an encrypted signature, so it's the MAC provides both. So this is actually for random padding, because remember we said that yes, random padding. Random padding is used for what? أتفكر؟
To make the packets in length.
بالعكس. لا لا لا. Random padding is different from padding in the protocol design. In the protocol design, we use padding to align the packet length, not necessarily to make it equal, but to align the packet length. But here, in fact, the purpose is actually to make the packet size different on purpose. Why?
Security.
To confuse the traffic analysis. Because as we said, for traffic analysis, if the packet size is the same, that's a piece of information that the attacker can use to, in fact, try to guess the key or try to break into the communication. So random padding is one of the features that we use to confuse traffic analysis. So here we in fact provide the random padding and we provide the length of the payload without the padding, so that we can reconstruct the payload and remove the padding bits. Okay, so that's provided for random padding. Other than this, so here this is the transport mode where we add the ESP header and possibly AH. Okay, and it works on top of IP. Whereas here we actually provide the header and then we add another. So here there is like 2 encapsulation stages. So we have to provide 2 encapsulation stages in the tunnel mode. Okay, because of the fact that we have to provide communication between the host and the router, and then in the router we have the start or the outbound traffic going into the tunnel. Okay, so in that case we have to provide 2 encapsulation stages. That's how it looks like in a layered model. So here in the IP, we actually provide. Here, I would say that IPsec here works on top of IP, not underneath IP, because the header is actually before the IP header. So in fact, IPsec works on top of IP, and this is logical and it makes sense because of the fact that IPsec is affected by all the features of IP being unreliable and so on. So it works on top of IP, right on top of IP. And for the transport mode, since we don't have to modify the source address or the destination address, we maintain the original IP header, in which case we do 1 encapsulation only to add the ESP and possibly AH. Here, on the other side, we have to do like 2 stages of encapsulation. So first, we encapsulate the ESP header and possibly AH, and then we have to add outer IP header, which stores the source IP and the destination IP of the routers or the firewalls that mark the beginning and end of the tunnel. Any confusion so far? Clear? All clear? Okay. That's in terms of encapsulation. So this talks about the ESP being used for authentication option. So ESP with authentication. So ESP inherently is used for encryption, right? But in IPsec we can always use it as well for authentication. So in this case, in this approach, the first user applies ESP to the data to be protected and then appends the authentication. And again, in terms of order, as we said before, whether you do the authentication first or the encryption first, does it make a significant difference? The answer is generally no. Although here we'll talk about it. The book tries to advocate the fact that if you do authentication first before encryption, it's better. But no, generally, as we will see later, even in other security services, it's done the other way around, and it doesn't make a significant difference. So if you do the authentication first, then you do it for unencrypted payload, right? But if you do the authentication second, then you have to encrypt the payload first, then you do the authentication for the encrypted message. And it doesn't make any difference because it has to be done in a reverse way on the other side. So the transport mode ESP, in this case, authentication and encryption apply to the IP payload delivered to the host, but the IP header is not protected, as we said before. Although, for authentication and for calculating the digital signature, we can include parts of the IP header, as we said, parts of the IP header. But some parts of the IP header we cannot include in digital signature, such as مثلا اللي هو انتوا قلتوا المرة اللي فاتت اللي هو time to live or the hop count, because that changes. If you use NAT, for example, then the IP also changes, right? So these fields that can be modified, we cannot include it as part of the digital signature, because if they change, then they invalidate the digital signature, becomes invalid, in which case we have to reject the packets. But this is done by design, so we cannot use certain fields in the IP header as part of the digital signature, right? But other parts can be used. Okay. So for the tunnel mode ESP, the authentication applies to the entire IP header packet delivered to the outer IP destination. Outer IP destination, or the IP of the router or the gateway on the other side, right? So in that case, we apply the encryption even for the original IP header. So the original IP header is hidden, so nobody knows exactly where this traffic is coming from which host. Okay, and the type of traffic is totally hidden from that tunnel. Okay, so the entire inner IP packet is protected by the privacy mechanism for delivery of the. So for both cases, authentication applies to the ciphertext rather than the plain text. So authentication is done for the ciphertext, although here the book, we'll see, it talks about the fact that if you do the authentication first, it's better. So, but in fact, it doesn't make a significant difference anyway. So transport adjacency, another way back to apply authentication after encryption is to use two bundled transport security association. So if you use ESP for both encryption and authentication, then you use one security association, right, for both. So it's one security association per header, basically. So if you use ESP for both authentication and encryption, then you have one security association. But if you use two different headers, then you need security association for each. Okay, which is what we call a bundled security association. Okay, so in this case, ESP is used without its authentication. Encryption applies to the payload. AH is then applied in the transport mode. So in that case, we will see graphically in a minute. In that case, you have logical security associations nested within each other. Okay, so encryption is applied to the payload. AH is then applied in the transport mode, in which case AH or authentication is applied to the encrypted message, as we said. Advantage of this approach is that authentication covers more fields. So if you do authentication after the encryption, we can, for the transport mode in particular, then we can, in fact, provide authentication for more fields. Disadvantage, of course, is overhead. If you do authentication for more fields, then it's more overhead. هنا بقى هو يعني إيه here the use of authentication prior to encryption might be preferable. That's what يعني إيه يعني we generally don't agree with, to be honest. Why? The book here tries to advocate certain يعني reasons for this, but these reasons practically they don't really يعني these scenarios don't really happen. So here it's impossible for anyone to intercept the message and alter the authentication data without detection, and that applies whether you do it for the unencrypted or the encrypted. So the fact that you do it for the encrypted message, again, any manipulation will be detected. So that's not a logical reason that justifies the preference of authenticating an unencrypted message. This one, it may be desirable to store authentication information with the message at the destination for later reference. That's very strange. And the idea here is that when you receive a message, you decrypt it, and then you authenticate the message. And then you store the message, okay, with the MAC. You sort of cache it, okay? So if you receive the same message again, it simplifies the calculation of this message. or it simplifies the authentication because you have authenticated this message before. That's from the application level. Why would you do this? Why would you send the same message from the application layer multiple times? I personally, I don't find any scenario under which you need to do that. You need to send the message multiple times with the same content, right? And in that case, the authentication is done once for this message, so you don't have to do the authentication again. I don't see the reason. I don't see a scenario in practice that allows you or actually encourages you to do that. And as we will see later, for TLS, مثلا, for example, TLS actually provides authentication for encrypted message, so there's no issue with that. ماشي?
Sometimes we send in applications heartbeat messages, which is just.
These are control messages. I'm not sure if this. These are control messages. We'll see. حتى ال TLS does that. TLS does that. We'll see this.
So I mean, this message is repeated just to say I'm alive.
Again, this is not traffic. Here we talk about application level messages, which is part of the data. But the heartbeats وكذا, these are usually used for control purposes, not for application data messages. I don't know. Maybe you're right, but I did not see a scenario under which you do this. And actually, in many books, they do not have a logical reason for this advocation, really. So they say it's mentioned explicitly that if you do authentication before encryption or encryption before authentication, there's no preference. There's no preference whatsoever. So one approach is to use by a bundle consisting of an inner AH transport and outer AR. شوف ده بقى this is a little bit interesting. يعني you can have different combinations for how you use the security association for AH versus ESP, which means that you can use AH in transport mode and ESP in tunnel mode. Okay, so in that case, in fact, the encapsulation will be a little bit interesting. So you have the payload, okay, and you can have the original IP header, and then you can use the AH in, actually no, this is, so here you can have the AH in transport mode, okay, and then you add the original IP, and then after this you add a ESP, and then you add outer IP, okay, because AH is done in transport mode and ESP is done in the tunnel mode. So in that case, you have to do the encryption first, the decryption first, to get the original IP address, and then you authenticate the packet using AH in transport mode. Okay? So theoretically, AH and ESP, because they use different logical security association, any of them can be used either in the tunnel mode or in the transport mode. Okay? But if you use any of them in the tunnel mode, then you have to provide outer IP. So that's what's described here. The result is that the entire authenticated inner packet is encrypted, which means all this part is encrypted. Okay. Type. So the concept of nested security association gives you different interesting scenarios. So here, for example, in case 1, we talk about using 2 security association, one for ESP and one for AH, and both are in which mode? Here? Both are? Yes.
Host to host.
Yes. So this is which mode? Transport mode. So both the security association for AH and ESP, both are used for transport mode, right? So that's the scenario that we talked about in the previous slide. Here, we have an interesting scenario. This is the nested security associations. So we have ESP and AH in transport mode, and we have another tunnel mode security association, okay, which uses ESP for both, which means that we have nested tunnels, okay? So we have a tunnel network to network, and we have another tunnel host to host, and these are nested together. Why would we want to do this in practice? In practice, why would we want to do this?
So it's encrypted even in the two internal networks. There is still some security between these different networks.
صح هو يعني having the tunnel, having this tunnel, okay, in the tunnel mode.
For example,
Hmm?
the tunnel is like when you use the internet, the open networks or something.
يعني صح, you're getting close. In fact, if you imagine مثلا مثلا you are sending a traffic through مثلا Ooredoo network. Ooredoo network uses some kind of a tunnel يعني for secure communication in their infrastructure. Okay, so in that case, there is some security policy that gets applied here. This security policy may in fact provide all types of behavior for your traffic that is going into this tunnel. It can block it, okay? Can block it completely. Or it can throttle it. Throttle يعني مثلا زي services like WhatsApp. If you have tried WhatsApp مثلا over Ooredoo network, you see the voice quality is really bad, صح? Okay? But if you establish a VPN, the voice quality becomes perfect. صح? صح كده? So because of the fact that if your traffic is exposed, then Ooredoo can apply some policy here, which it detects the service, okay, and based on the service, it provides certain behavior, right? So it decides to throttle the traffic, block the traffic, things like that, okay. But if you use a tunnel host to host in the transport mode, then your traffic here is hidden. Is hidden. So the service is not detectable. Another برضو behavior is that for certain types of traffic, especially it happens here مثلا. In this case مثلا, you have again a tunnel mode between a host and a network, and there is another transport mode security association between a host and a host. Why would you want to do this? So again, if you have some VPN connection from your host to access a network securely. مثلا if you want to access مثلا the QU network from a hotel مثلا in the US, right? So you have a tunnel mode VPN connection between your host and QU network, right? So certain types of traffic here might actually be bypassed. يعني مثلا you are trying to send a traffic, and somehow the policy here bypasses that traffic. Okay, the traffic goes away from the tunnel, but you want to actually secure that traffic. So depending on the application, the policy that gets applied here might in fact bypass that traffic from the tunnel, which means that it sends it to the internet non-secured or unsecured, right? If you want to force that traffic to be secure, then you can in fact create another tunnel in the transport mode, which means that you force that traffic to be secured. Okay, فهمنا كده? So that's when you use that concept of nested security association. Of course, this mode is straightforward. Is a tunnel and use ESP only. Okay, for both authentication and encryption. So in that case, we have one security association in the transport in the tunnel mode. Okay, so these are the different combinations. So in a nutshell, ESP and AH use different security associations, and they can be nested in any combination that you need. Okay, and for each of these cases, you may have different features or different behaviors, providing secure communication, different behaviors. One question that I got before, which was kind of interesting. So if I do this, isn't that considered like a security breach? So يعني احنا we are breaching into the Ooredoo network, and the answer is no, because here the purpose is not to attack or not to احنا بالعكس انت you want to hide your traffic, okay, you want to hide your traffic and giving the guarantees to the Ooredoo network that my traffic is actually hidden because it's secure. Because the original objective of IPsec is to secure the network infrastructure. So if you use VPN or security, then خلاص, there's no harm of this مثلا application or this traffic providing any مثلا security breach to the network infrastructure, and that's what you really want to achieve. Yeah. Okay, so there's no security breach here. طيب, so that's the end of this topic. Now بقى, as we said, if we search through the security policy database, and then we have the SPI, but we don't have a match for the security association, then we have to trigger the internet key exchange to establish a security association. Okay, so that internet key exchange provides بقى user authentication. The ultimate goal of this is to again get like a sort of a master key. From that master key, you get the session keys, and you get all the session keys بقى for encryption, for ASP, for AH, for all types of algorithms that are used for MAC, for encryption, for everything. Okay. So the key management portion of IPsec involves the determination and distribution of secret keys. So a typical requirement is 4 keys for communication between 2 applications. 4 keys ليه بقى؟ يعني احنا قلنا it's logically one direction. So 2 keys in that direction for encryption authentication, and 2 keys in that direction for again encryption and authentication. ماشي؟ So IPsec architecture document mandates the support of 2 types of key management. So key management can be performed manual. So manual can be done if you want to, for example, as we said, if you want to secure just 2 offices, if you want to build a tunnel, مثلا, to secure the communication through 2 offices, that's it. Okay, so in that case, the system administrator can in fact go manual in each of these offices, and he or she configures these keys, builds that keys, okay, or builds some kind of a certificates مثلا that can be used for authentication between the 2 offices. So everything is configured manually. So that can work if you have a very small network, maybe office-to-office communication, okay, and it's static. So you're not expecting any dynamic changes or any kind of modification to that system. So in that case, the manual configuration might work. But of course, if you have a distributed system where you have offices distributed all over the world, then that becomes really prohibitive, in which case you have to use an automated way, and that's what we need to talk about. Okay. So in that case, we enable the creation or the negotiation for security association on demand. Okay. So for automated authentication and key management, IKE defines 2 different components. Again, in IPsec version 1, they kind of separate these 2 components together in the standards. But again, in IPsec version 2, they started to combine both. And as we will see, in the protocol handshaking, they are actually interleaving together. So the protocol handshaking, in fact, covers mainly IPsec version 2. But separating those 2 components, here we talk about Oakley Key Determination Protocol. So that, in fact, talks about the key exchange using Diffie-Hellman. So Diffie-Hellman, as we said, based on the discrete logarithm. So we have alpha and q, and alpha has to be a primitive root of q. Remember, we talked about this, right? So we have to have Diffie-Hellman to negotiate a shared key between 2 parties, the initiator and the responder. They call it the initiator and the responder. I don't know why. This is the terminology that's being used. There's one drawback in Diffie-Hellman. We talked about it, which is Diffie-Hellman قلنا there is a drawback in Diffie-Hellman, right? There's an inherent drawback in Diffie-Hellman. اللي هو كان لا It is fairly complex, of course, because the calculation of the discrete logarithm is kind of complex, yes. It is complex, but that's not يعني a drawback or a problem. The problem is إيه بقى؟ Diffie-Hellman is inherently prone to إيه بقى؟ Man in the middle attack, bravo عليك. Right? We said that if I can send a public key to a host or to Alice or to Bob, I can force Alice and Bob to engage into calculation based on the public key. They can calculate the shared key and so on. So a man in the middle can in fact provide. So there is another problem here, which is what we call again clogging attack. Clogging attack is a denial of service attack. I can actually in fact provide public key from multiple يعني كمان from multiple sources. So from one مثلا attacking workstation, I can launch a distributed attack and try to forge the IP address, providing يعني denial of service attack for a node, to have the node always engaged in calculating a shared key based on public keys. So imagine this can break the host completely. So that's why the Oakley key determination, Oakley here is the name of the scientist who actually came up with this. Oakley key determination protocol here is based on Diffie-Hellman, but with some but providing some added security. Added security here tries to address the idea of man-in-the-middle attack and the clogging attack. Okay. So that's the key here. This is that part, and this is generic. It does not depend on whether you are using tunnel mode or transport mode. This has nothing to do with this. Whether you're using ESP or AH or both together, this is generic to all of this. So this doesn't have anything to do with, what type of format of the messages or headers or anything like this. And there's the Internet Security Association and Key Management Protocol, or what we call ISAC-MP. This ISAC-MP provides the framework for the management of the keys and the security association specifics, which includes the ESP or AH. It gets into the specific negotiation for the security association for ESP and AH and so on. Okay. So these are the two parts. ماشي؟ طيب. So what are the features of the key determination protocol or mechanism? Actually, I would call it a mechanism. So as we said, it tries to address multiple issues here. So it tries to address the clogging attack. So clogging attacks, as we said, we are trying to forge IP address to provide public keys from different directions coming to the same host, so that the host can be engaged in calculating shared key based on the public key, based on the discrete logarithm. And as we said, this is fairly complex. So if we do this unnecessarily from different sources, that will consume the resources of the node. So to mitigate this, the Oakley, the scientist, he came up with the concept of cookies. And cookies here is different from the web cookies. Cookies here is just a mechanism. Actually, the details of this mechanism is not actually detailed in the book. You don't have to really know the entire details of this. But cookies are actually, in fact, based on certain token, which is a hashed value based on the hard coding, the IP address of the source and the destination and the port, together with some secret value, which is based on the timestamp. And this is done in a way that, if you try to forge the IP address, then this cookies becomes invalid. So it's similar to the token that we talked about in Kerberos. So if you try to launch or forge the IP address from different directions, then in that case, the cookies becomes invalid, and the message will be rejected. Okay, so you will not get engaged in unnecessarily calculating the shared key based on the public key. And that's the main objective, okay? So if the message is coming and the cookies is invalid, then you don't engage unnecessarily in calculating the shared key based on the public key, right? So that's for the clogging attack. But this is but this will not fix also. This will not provide complete authentication for the node. So for that, we have to use some authentication mechanism as well to mitigate the man-in-the-middle attack. Okay, so for clogging attack, we use cookies. For man-in-the-middle attack, we use authentication or message authentication. We talked about that. So the technique that is used as part of this Oakley determination protocol for authentication is to use certificates. We are using certificates to authenticate the messages and to mitigate the man-in-the-middle attack. Type. There's also the replay attack. صح? There's also the replay attack. So if I copy the same message and send it again. For that, we use the concept of nonces. Nonces are, again, these are pseudo-random numbers generated, and these are generated in a way that becomes unique. It's called number used once. Okay, so for each message, we generate a unique random number, okay? So to try to mitigate the replay attack. So if you use, because this is actually hidden, so if you try to copy the message and send it again, then so we detect that as a replay attack. So one thing we notice here, and that's actually برضو an interesting question. So we talked about the fact that for replay attack we use the window mechanism, صح? So why are we talking about nonces here? ما احنا قلنا we use the ما عايز الناس تبقى صح يعني. Don't just يعني accept everything كده خلاص يعني. احنا اتكلمنا عن window technique صح؟ So here we're talking about nonces for replay attack. Is that a discrepancy?
It was for IB6.
طيب ما صح ايوه so صح كلامك صح ايوه بالظبط صح كده صح احنا we're talking about the window mechanism as part of securing the data traffic for mitigating the replay attack as part of the data communication, right? But here احنا we did not start data communication. احنا we're still talking about security, establishing the security association before the data traffic, right? So in that case, we have to use a different method. And here, we're using the A nonces. And why not مثلا window technique? Because here we're not talking about data. These are just control messages for establishing the security association. So these are like four-way handshake, as we will see. Four-way handshake, so it doesn't really require a window mechanism per se. So ماشي كده? So إذن nonces for replay attack, cookies for clogging attack, mitigating يعني clogging attack, and we use the certificates or authentication for mitigating the man-in-the-middle attack. So these are the security added on top of Diffie-Hellman. Other than this, Diffie-Hellman is being used as the underlying mechanism for creating the shared key out of some exchanging public key. Okay. Yes, another interesting thing here, which is kind of unique to IPsec, is the use of what we call Diffie-Hellman group. This Diffie-Hellman group represents some kind of a level of security, if you will. Diffie-Hellman group here uses مثلا يعني ممكن نقول ايه مثلا Diffie-Hellman group 1 uses a public key of size 500 bytes مثلا. And Diffie-Hellman group 2 uses 1024 bytes. What is the difference? The difference here is that if the public key size is large, then the shared key size will be large, صح? In which case the security level will be more. Okay, so this Diffie-Hellman group gets negotiated between the initiator and the responder. So we have to negotiate some kind of a Diffie-Hellman group. So there are some predefined Diffie-Hellman groups as part of the standard. So the initiator sends some kind of these are the available Diffie-Hellman groups that I can use. Then the responder would say, okay, so I can use this Diffie-Hellman group, and based on this negotiation, they can negotiate a Diffie-Hellman group for each direction. Okay, so a Diffie-Hellman group here refers to some level of security. And as we will see, so Diffie-Hellman group 1 entails the fact that the public key size will be this, the security, the encryption algorithm, for example, will be triple this. The authentication mechanism that we will use will be مثلا HMAC or whatever, and so on and so forth. So it's a whole specs of security mechanisms that are associated with each Diffie-Hellman group. ماشي؟ اتفضل.
The shared key size, it doesn't depend on the.
It does.
It does.
It does طبعا طبعا. ما هو shared key size is the discrete logarithm of.
By using the
Yes. So if the public key size is large, the shared key generated will be large. Yeah, it's proportional يعني. ماشي. So this is بقى the handshaking. And طبعا يعني هو it looks a little bit messy, but احنا we can simplify it. Again, we don't have to memorize all these messages, but we can just simplify it and focus on the high level aspects. Basically, this part tries to negotiate the security association for the data traffic. Why we say that for the data traffic? Because there's also security association, which we didn't talk about before, for the management traffic. What is this management traffic, Bam? So, as we said, this is the initiator, and this is the responder. I'm using the same terminology in the standard, yeah. Okay, so as we said, if we try, this initiator is a generic term that might represent the host for the transport mode, or the firewall, or the router for the tunnel mode. So here we have a data, we have to establish a data tunnel. Whether this is ESP or ASP and AH and so on and so forth, then there is some security association here, right? But as we said, as part of this data traffic, we have to use the window mechanism, right? Based on this window mechanism, we have to watch for some kind of replay attacks. In which case, if we discover some replay attack, then we have to sort of notify the responder, or the responder can notify the initiator. Based on that, we can decide to delete the tunnel, renew the security association, things like that. So from that, we can imagine that we have some kind of a control that has to go in parallel to this data traffic. And that's because of the fact that IP, again, all of this is based on the fact that IP is unreliable and it's connectionless. It does not provide any state or any kind of control. So we have to have, in order to have security services on top of IP, we have to provide some kind of control level. So IPsec uniquely يعني برضو provides some kind of logical very small logical channel for managing the data tunnel. Okay, so this management tunnel is used to sort of notify the responder that there is some security breach or some possibility of replay attack. Delete that, or reconfigure that tunnel to use another security association specs, things like that. So here, these are the types of messages that can be sent over this management tunnel. Okay?
Why I have to create a management tunnel and security for no data? It's only for it's a tunnel. It's
Yes. So why we don't use the same tunnel for control and management? Is that?
Or I can use the normal network without using a tunnel or any security.
For management also.
Yes.
هو the idea, this is the design choice for the standards, is that the management traffic has to be separated logically from the data traffic. لأن المساges that are used for management, they don't have a specific payload or specific data. They don't have like data يعني content. Okay, so they separate it logically from the tunnel itself. And that concept, by the way, we will talk about it again for TLS. TLS, we use the same concept. Even with the fact that TCP is connection oriented and so on and so forth, but we have to provide some kind of a high level control over the data tunnel. And usually this control is kind of separated from the data traffic. Okay? The fact that it's separate, it requires the fact that you have to have a security association, which means some specs for encrypting and securing the management messages, which is different from the data traffic. Because if you assume, like for example, if you have a security breach in the data traffic, okay, this means that the data tunnel has been breached, right? صح? So because of the replay attack or something like this. So in that case, if we use a separate logical channel for controlling this, then the assumption here is that the control channel is not affected. And we can sort of renew the data security association without actually destroying the control, which means that the session itself or the communication can still go on, okay, without disruption, okay? But we just need to renew the security association. So this, if you separate logically the management from the data, this can happen seamlessly without disrupting the communication. So this is the assumption, yeah. Not sure if this is, yeah.
No, what is the purpose from securing the management? Why I have to secure?
Securing the management? ما هو securing the management so we the
The messages that I have to secure during the management between these.
ما هو still the management control messages, these are messages that have to be sent, for example, to notify the responder or to notify the initiator that there is some kind of replay attack. So these messages has to also be secure. Why do you think it can be sent?
What is the kind of attack that can be on these messages?
Similar to any kind of data attacks, because again, I mean, if you assume that you don't have to send these messages every so often, then I might agree with you. But because of the fact, again, that IP is unreliable, these types of messages can be sent very frequently. So for example, here, you have to change the configuration, or you have to notify the responder that there is some مثلا replay attack or possible replay attack, or you can delete the security association and renew the security association. So there are some possibilities that you can renew the security association if the lifetime is expired, or if there is a possibility for replay attack. Okay? So these messages have to be sent kind of regular. Okay? So, so the assumption that these have to be sent in a separate channel is justified because of the fact that if you have any replay attack for the data traffic, then you can seamlessly provide some renewal to the security association without affecting without providing any service disruption. Okay? And again, we'll talk about this again in TLS. Because this control channel provides some kind of a session level control. Here, we're talking about a connection level data traffic. I can change the configuration of the connection, but keep the session going. Keep the session itself going. Okay? I can provide any changes to the connection as I wish. Maybe on regular basis, I can change the configuration. I can provide some security association renewal. I can do this. I can delete. I can notify. I can do this and that, right? But this session is continuous. So in that case, it's and this is the same concepts used in different security services, separating the control or the management session provides some kind of continuation to the service. So we don't have service disruption. I'm not sure if you are convinced with what I'm saying, but in any case, yeah, that's what's defined in the standard, yeah. And I'm trying to give you a logical reason for why this is happening. And again, we'll talk about the same thing in TLS. In TLS, it becomes even clearer, yeah, inshallah. So all of this, all of this discussion, gives a rationale that because of the fact that this management traffic is required to be logically separated and secure, this means that we need to have a security association for this management traffic. Okay? So that's what's negotiated here. This is the security association for the management traffic. So this is to negotiate the security association for the management traffic. Okay? And this is, in fact, the management traffic. Okay? So the management traffic can provide different types of messages اللي هم هنا. Notify, delete, configuration. In fact, in the standard, there is a bunch more, right? So these are the possible messages that can be sent on this management tunnel here to provide some kind of reconfiguration, notification, delete, security association, renew security association, and so on and so forth. Okay? The data traffic itself is not in this picture. The data traffic itself, اللي هو هنا, is not in this picture. Okay? واضح كده? So that's the whole picture. So digging more بقى, into each of these. So we see here that in each of these messages, we have a header. This header here provides the اللي هو ال IKE header. IKE header here contains basically the cookies to try to, again, mitigate a clogging attack. Okay? And then here, the initiator sends to the responder SAI1, ASAI1 here, SAX1. I here stands for the initiator. SAX1 here offered and chosen algorithm in Diffie-Hellman groups. Here we provide the negotiation for what kind of algorithm are we going to use and what Diffie-Hellman group are we going to use. واضح? So this is the Diffie-Hellman group. Diffie-Hellman groups here that the initiator is going to use entails or reflects the level of security, okay, that the initiator wants to use to communicate to the responder. And then there is the NI here. NI here stands for nonces. Nonces is for mitigating the replay attack. Other than this, we have the Diffie-Hellman public key. Public key, again, yeah. So we have the public key, which is the initiator sends to the responder the public key in order to calculate the shared key, right? So we have alpha and Q already, and we use the public key to generate the shared key. So here, we mitigated the clogging attack. We mitigated the replay attack. We provided the public key. So here, the responder can calculate the shared key based on the public key if the cookie is valid. In this message, the responder will send back saying that, okay, so I can give you the cookies from my side to validate it. I can negotiate certain Diffie-Hellman group. I can give you the Diffie-Hellman public key from my side, but you have to authenticate yourself first. So it sends a certificate request for the initiator to authenticate itself using certificates. So here for authentication, we use certificates. Authentication is used to mitigate a man-in-the-middle attack. But at that point, here we have a shared key which can be calculated on both sides. صح? Because we have exchanged the public key on both sides, so now we can have a shared key. This shared key from now on can be used to encrypt all the upcoming messages. The upcoming messages will be used for authentication as well as for providing security association specification. They are including all the specs for the security association here. ماشي? And then from the other side as well, we provide the certification, the certificate for authentication, and to provide the security association specs. So here we have a security association on each side established, and this is for data traffic. And then we have the same shared key. We can use the same two-way handshake to do the same for the management traffic. So this is the security association for the management traffic. Again, using nonces, using the same concept that we have done, except that here the security association is different. This is used for management traffic. And once we establish the management traffic, the management security association, then we can, at any point of time, use a message on the management security association or the management tunnel to notify, delete, reconfigure, things like that. ماشي? Again, the data traffic is not in this picture. ماشي كده؟ So in the standard بقى they define اللي هم ال Diffie-Hellman group. This is actually the Diffie-Hellman group. So here we see two RFCs. Each of these RFCs, they define the Diffie-Hellman group for certain logical part of the world. And basically, here we provide RFC 4308, not that we need to memorize it, يعني, provides the specification for the Diffie-Hellman group for all parts of the world except for the US. اللي هي ال NSA كده اللي هي ال National Security Agency اللي هي part of the US. So in the US, there are different specifications for the Diffie-Hellman group. So here we have two Diffie-Hellman groups, or two groups, يعني, VPN A, VPN B, only two groups. And as you can see, for group A and group B, so we notice here is that here we use triple DIS, here we use AES with cipher block chaining. So to provide higher level of security or more security, okay? And here we use مثلا ال group size or the public key size 1024. Here we use 2048, okay? So that gives you a higher level of security. For the US, they kind of define two different specifications. This is for classified traffic. Used for مخابرات كده يعني. ماشي? And this is used for public traffic. So you have two different levels of security for classified or unclassified traffic. يعني. So that's what the standard defines. Okay? So any question in that part? So when we talk about TLS, we'll talk about the same concept, but يعني we'll see some differences, of course, based on the features of TCP in that case, not IP. So as a summary for the IPsec here, we talked about IP security overview. We talked about the benefits of IP security, providing secure communication between networks or between hosts. We talked about the IPsec architecture and standard documents for ASP, for AH, for policy, for security association, and so on. We talked about two different standards, encapsulating security payload and authentication header. And we talked about the transport and tunnel mode. We talked about how we can combine the security association using the bundled security association and for what purposes exactly. And finally, we talked about the internet key exchange, which is used for negotiating and establishing the security association, both for the data traffic and the management traffic. ماشي؟ Okay. طيب. So transport layer security here talks about securing بقى ايه؟ network to network ولا securing ايه؟ Not even host to host. Application endpoint to application endpoint. Because that's what TCP is used for. صح? TCP is used for communication between two application endpoints. ماشي. So TLS here works on top of TCP. On top of TCP معناها it inherits all the features of TCP. So TCP is reliable, TCP is connection oriented, and so on and so forth. And that actually affects بقى ايه how TLS will work in terms of, you don't have to have window mechanism for replay attack because everything is ordered and it's connection oriented. You don't have to provide one way because it's actually bidirectional. So one security assertion here, we don't call it security assertion, we call it cipher spec. So the cipher spec will contain all the security context for bidirectional communication. So all of this is actually inherited from the features of TCP.
So TTLS is the same or
Yeah, TTLS is tunnel TLS, which is used to again provide security over UDP بقى, not TCP.
okay.
فايوه فهتلاقي بقى differences. And that's a good point. If you work on UDP, it's different from working over TCP. The implications are different, صح? Because UDP again like بقى IP. هتلاقي some similarities بقى between TTLS مثلا and IPsec مثلا. You will find some يعني overlap, some similarities. But again, TTLS still provides security between two application endpoints, مش network to network, which means again that here we don't have to have policy database per se, right? Because we don't have different traffic. It's only application traffic. It's only application coming from one type of traffic coming from one application. So here we don't have a security policy database per se. We don't have that. صح؟ معايا يعني okay. So the World Wide Web is fundamentally client server based and it's application level. So the TLS or actually SSL اللي هو secure socket layer has been introduced to provide security services for World Wide Web originally for World Wide Web. Okay. بعدين TLS came into the picture to try to kind of deprecate SSL and trying to introduce security services which works for web traffic or non-web traffic. And that's why مثلا we have TLS built in our email clients, right? So TLS came to become more general purpose for web or non-web traffic and tries to deprecate SSL. But we'll see about what happened يعني. طيب, why did we need to provide special security services for web in particular? Not that for any type of application, for web in particular. يعني web in particular because of the widespread use of web. Similar to على فكرة برضو the same يعني mindset similar to موضوع الوايرلس برضو. يعني the World Wide Web is very commonly used, right? It's used by even 3-year-old kids مثلا. They use the World Wide Web, صح? It's widespread usage. So there are some, again, characteristics for web that motivated the introduction of special security services, similar to wireless برضو. One of them is that web servers are relatively easy to configure. Why? Because احنا هنا the World Wide Web deals with exposed text. It's text-based, صح? In fact, if you go to any page and say view source, you will see JavaScript code, you will see everything, صح? All the content of the... So it deals with exposed text, right? So the web content is increasingly easy to develop because of the fact that it's text-based. The underlying software بقى is extraordinarily complex. So in order to make the web content very easy to develop, it's text-based, we have to provide an underlying kernel in the web server that's very complex. And that's, in fact, برضه the same concept of مثلا, يعني مثلا if we try to talk about another example similar to this, which is Java مثلا. Java has been introduced to provide برضه the inherent feature or fundamental feature of being a portable through different platforms and stuff like that, and very easy to develop, and it's fast to develop, and so on and so forth. But in order to provide that convenience, we had to build a complex اللي احنا بنسميها ايه Java virtual machine. صح? This virtual machine sort of separates the Java from the platform, okay, and tries to provide that interface. So Java itself is simple to develop, but the Java virtual machine itself is complex, and it deals with some low-level issues. And that's the same idea here, okay? That kind of configuration makes the web content very easy to develop, and in fact, it can be used by 3-year-old kids, or untrained users, okay? And using that text, you kind of interface to a very complex platform underneath. So that triggered or motivated the attackers to try to use that convenience and simplicity in the text to try to design text to try to find some flaws and some issues in the underlying platform or web server. So you can freely develop your text in a way to try to discover all the attack surfaces in the complex underlying platform. واضحة النقطة دي؟
Like SQL injection?
Yeah, SQL injection or يعني مثلا if I can مثلا design a certain مثلا text to breach into the web server and discover some security flaws, right? So now I have a security compromise in the web server. I can use that to harm بقى anything. يعني I can provide even network injection. يعني I can do whatever I want. واخد بالك؟ Because it's a simple text, مثلا using JavaScript, ماشي? And the underlying web server platform has certain security flaws, right? So I can use that JavaScript to penetrate through the web server and create some attack surface that I can inject any kind of attack to the application or to the system. So this complex platform for the server hides many potential security flaws. So no matter how يعني much you become يعني طبعا ده بقى related to software security بقى. The web server platform is related to software security. ماشي? So a web server can be exploited as a launchpad بقى. As a launchpad معناها بقى ممكن you can do بقى SQL injection, you can do even network injection, you can do whatever. This can be also the World Wide Web can be used by untrained users and common clients for web-based services. And these untrained users, يعني you can get trapped easily. You can navigate from one website to another. You click on a link, and of course you're not trained that this link has some potential security issues, and you can harm the entire web server, which affects the entire workstation that you work on, and from that it can be used as a launchpad to even provide some attacks to even the network or to the file system or something like that. So again, very easy text to develop. The underlying platform is very complex and it has some potential security issues, okay? And that text is used by untrained users, so that can provide a recipe for lots of security issues that can be abused. ماشي؟ طيب, so there's nothing new here. So these are the type of threats and the consequences and the countermeasures. We talked about that before. So integrity, for example, provides some kind of or requires some kind of active attacks to manipulate the message. So modification of the user data or Trojan horse browser or modification of the memory. So you need to provide some integrity checks not only on the level of the data, but in some cases on the memory access level. And the consequences of that, you can lose information, you can compromise the machine, providing some active attack and compromise. And the countermeasures are usually to use by some cryptographic checksums or MAC, layer message authentication codes, or some level of authentication to mitigate any kind of active attacks. Confidentiality, same thing, requires some kind of passive attacks, and you can use encryption. So here, by denial of service attack, if you notice here, difficult to prevent. Yani, countermeasures for denial of service attacks is always yani very tricky, especially for web servers, because just the fact that the web server receives millions of messages, even if these messages are illegitimate messages, just by filtering these messages to classify this message as illegitimate message requires huge amount of resources from the web server. Okay, so that's very difficult to prevent in many cases. ماشي. So there's nothing new here. In terms of layer stack, as we said, IPsec itself usually is implemented or integrated in the operating system itself, which means that it's seamless and agnostic to whatever application. صح? So applications do not actually see whether they are using IPsec or not. They don't care about that. So IPsec itself is built, in the operating system level, right? Kerberos, on the other side, as we said, Kerberos as a key distribution security is actually integrated in the application level. ماشي? So it's integrated in the application level. طيب, SSL and TLS has an interesting situation because it can in fact be integrated in the operating system. It can be integrated in the operating system, or it can be integrated in the application itself. Okay, so the operating system, if it has TLS, then the application, all it needs to do is just to say, "But I want to use TLS to secure the traffic," or TLS can in fact be integrated into the application itself, which means مثلا in the web browser. So مثلا Chrome or any kind of browser or Edge or something, they have built-in TLS. ماشي? So it can be built in the operating system, which means it can be used by مثلا email client or any other application, or it can be built into or integrated into the application like web browsers. ماشي? So that's what this slide tries to see. So as we said, before TLS, there was SSL or secure socket layer. So secure socket layer was in fact used very commonly in web browsers, and SSL was in fact integrated into the web browser. SSL was not actually integrated in the operating system. It was part of the web browsers. Then TLS, at least TLS version 1, historically بقى, came with the perception of trying to deprecate SSL. So it tries to force مثلا الvendors و everyone يعني to deprecate SSL and tries to use TLS version 1. That's why TLS version 1 was not backward compatible. So backward compatibility was not part of TLS version 1, to try to force people to deprecate SSL and start to use TLS, because it's general purpose. It can be used for web browsers and any other application level traffic. It can be built into the operating system. It can be used by web browsers and other applications seamlessly. So there's no need for SSL. So when you say HTTPS, you can trigger TLS normally. ماشي? But that failed miserably. that concept failed because people they still kept SSL integrated into many of the web browsers. So TLS version 2 has been upgraded or modified to become backward compatible with SSL. So they become compatible with each other. So TLS and SSL are used interchangeably, but TLS is more general purpose. SSL is used exclusively for web content, but TLS is general purpose web security security services for all types of applications. So TLS is general purpose service implemented as a set of protocols that rely on TCP. So TLS works on top of TCP, not UDP. For UDP, there's different security service. So TLS either provided as part of the underlying protocol suite and therefore be transparent to the application. That's what we have, underlying protocol suite, which means it's built, integrated into the operating system. Or TLS can be embedded in specific package or application. So طيب خلينا نوقف عشان ده يعني this slide will have to spend at least 10 to 15 minutes to talk about it. So this is the protocol يعني suite for TLS. It needs يعني a lot of